everybody, and welcome. This is the introduction video for Science 110, Principles of Science at Sandhills Community College. I am Brennan Brown. I will be your professor for this semester. One of the things I like to tell my students up front is that Brennan is my middle name. Stephen is my first name. I go by my middle name, and Sandhills has it input a couple of different ways in the system. If you get an email from Stephen Brown, me and him are one and the same, and that email probably pertains to Science 110, Principles of Science. My contact information is listed there. My office is in Meyer Hall 203. That's upstairs Meyer Building on the Pinehurst campus. My phone number is 910-695-3759, and my email is brownb@sandhills.edu. Feel free to contact me in any of those listed ways. I'm usually on campus from 8 until about 4, Monday through Thursday. See me anytime in my office during those hours. And I love it when students come by in these online courses. Sometimes we don't get to know each other as well as I do, obviously, the face-to-face students, but all of my students are welcome to come by, ask questions, talk about the course content, or just talk about science and education in general. If that's something you would like to know, do and get to know each other, please feel free. The best way to reach me is probably the email address down there. I do have it sent to my phone, and I try to answer students' questions and emails within about 24 hours, if not a lot earlier. Sometimes it's the same day, but within at least 24 hours, I'll try to have you a response anytime you send me an email. So please use those routes of contact to let me know how the course is going for you. Let me know whatever questions you have. I'm always here to help. I like to make sure my students are getting all of the available resources they can to be successful in the course. If you'll follow along with me in the rest of the video, we'll talk about what we're going to learn and give a brief survey of the topics we will cover in Science 110. Moving along, here we see some of the learning goals that we have for Science 110 this semester. One of the things that I really hope you can answer when you leave this class at the end is, what is science? Understand that there is no exact answer to this question. It will differ from individual to individual, but all answers would share some common characteristics. And we find out the same thing about certain branches of science. Geologists and biologists have completely different tools, sometimes completely different methods. However, we both consider both of those things science, and they are performed both by scientists. We want to understand what makes them science, what characteristics and methods they share, so that we can learn to identify when science is being used. When we're able to identify when science is being used versus when it is not being used, we probably will become better at learning goal number 2, trying to figure out what separates science from pseudoscience. Pseudoscience is a claim or a product that uses science-sounding terms to sound legitimate, but perhaps has not been tested as well as it is made to seem. People use pseudoscience to do things like sell products that haven't been tested for efficacy or safety. They also may use it to try to make it seem like an individual or a group has extra natural or supernatural abilities. And while these types of things very often are benign, if ineffective, sometimes they can be harmful. There have been examples of people using pseudoscience to sell products that have harmed people, up to and including the loss of human life. So being able to separate and identify when something is true science versus when something is pseudoscience is a skill I hope you either gain or become better at by the end of our course. The next 2 goals: what are some ways science impacts the world around us, and how we evaluate scientific claims so we can make informed decisions for ourselves, are somewhat correlated. And from both of those, what I hope you can take is, as you move through your life and you encounter situations where some scientific knowledge would be beneficial to help you make a decision. I hope you can look back on this course and say, oh yeah, I learned in Science 110, or I learned in that science class I had that this fact is true and this is supported by evidence. And that means that you will be able to determine for yourself when a piece of evidence for a product or a procedure or something like that is worthwhile and worth believing. And so that is a couple of the other goals that I have for this course. Finally, down there at the end, you can see while I don't want the overall complete focus of the course to be on rote facts and figures like you may expect from other science classes in the past, we will do some of that type of work, and we will look at some science through that lens. Specifically, we are going to survey the three major divisions of the natural sciences. That is chemistry, biology, and physics. College classes typically run 16 weeks, so we take about a 5-week look at each of those three major natural sciences, and we kind of cover broadly some of their more common topics and learn what scientists are trying to learn and understand in those three branches of science. We'll move along and talk about the schedule and types of assignments that you will be expected to keep in the next part of the video. And as I was saying, here are a list of the assignments that you will be expected to complete in Science 110 this semester. When you open the Moodle page, you will see a page filled with units, much like you see here on the right side of the screen. The units have their weeks labeled, and you'll notice there's one for every week. So all you have to do is come in and complete that week's unit, and as long as you're keeping up with that, you will be okay in Science 110. So when you open those units up, you will see a couple of things. The very top will have the resources for that unit. The resources will include things like a video, like you're watching now, either of me giving some notes and some explanations. I will often also include other videos from around the internet. I will include reading selections for you to read, and I will try to include some simulations for you to interact with as well. So you'll want to start your week by opening those resources, paying attention to the notes and things I say to look out for, and trying to get that information by interacting with those resources. Once you've taken some time to view them, you'll want to attempt the assignments that are due every week. So you have 3 assignments within each unit. Every unit is going to have a discussion board, a lab exercise, and a lecture assignment. I'm going to talk about the discussion boards first because those are the first ones that you have to do. Every week by Wednesday, you'll need to go in and click the discussion board link. The discussion board link will bring you to a page where I have posted a video or an article to read or something of that nature and a prompt for you to respond to after viewing that resource. I generally ask for responses to be about 200 to 400 words. Those need to be completed every week by Wednesday at midnight. You are not done with the discussion board post at that point either. Everything else is due Sunday at midnight, including 2 responses to your peers on the discussion board. Please make sure you are responding with more than just, I agree with what you said here. I will have more information within each discussion board. Then you will also have a lab exercise every week due by Sunday night. These will utilize the materials that you picked up in your lab kit from me, and I advise not waiting till Sunday to look and see what you have to do. When you click the lab exercise assignment, you will find some instructions either in text or video form for you to view and follow. You will also find an assignment of questions for you to answer and respond to. These generally take 1 to 2 hours, sometimes a little less, in a couple of cases maybe a little bit longer. So I would be sure that you are starting those before Sunday evening when they are due. The last assignment that you have is going to be the lecture assignment. So that's going to be kind of a standard Moodle quiz where you go in and answer all types of questions, multiple choice, fill in the blank, match, and so on and so forth, that that relate to the resources from the beginning of the unit there. So by viewing those videos, reading those responses, you will definitely be able to answer all of those questions. Those are due on Sunday at midnight as well. However, you have unlimited attempts on those. So I would be sure that I am trying them before or sometime at the beginning of the week before Sunday, so that you can get as many opportunities to go back and review those resources, because you will be given the highest grade that you earn after however many attempts you want to attempt. So those 3 types of assignments are due every single week. We will take some exams for each of the 3 types of science that we discuss in Science 110. You can find those exam schedules on the schedule of assignments on Moodle. You will see that they have an open time of 1 week. So they will open on 1 week on Sunday, and you will have until the next Sunday at midnight to find yourself some time to sit down and complete those exams. Those will, unlike the lecture assignments, those will have a time limit, and you will only get 1 opportunity at answering those. However, they are open notes, so take that for what you will. If you don't do so hot on one of those and you would like another attempt, or you would like to replace that grade, I do offer a cumulative final. It is not required. However, if you would like to replace a test grade with you may take the cumulative final and try to replace one of your test grades. Averages are determined with the following weights. So the lecture assignments are worth 40% of your final average. Lab assignments are worth 25% of your final average. Discussion boards are worth 20% of your final average. And the exams are worth 15% of your final average. At the end of the semester, I will average everything with those weights, and Science 110 is graded on a 10-point scale. So anything between 90 and 100 will earn you an A. Anything between 80 and 89.9 will earn you a B. Anything between 70 and 79.9 will earn you a C. Anything between 60 and 69.9 will earn you a D. And anything lower than 60 will be recorded as an F. Over the next, now moving on a little bit, we'll talk about some of the early information about how we're going to define science. Alright guys, let's get kicked off here and start talking some science. So I said in a previous slide that one of the things we're going to try to do is answer the question, what exactly is science? If I went and asked a bunch of people that question, what do you think science is? I'd probably get some answers that look like the pictures here behind me. Some people may talk about volcanoes. Some people may talk about some chemicals or medicine. Some people may talk about biology, like you see in the lions on the savannah up there. Some people may talk about all of the great technology that we have in our present day and age. Some people may talk space, stars, and rocketry, like you see there in the galaxies. There's a lot of answers. There's a lot of things that science studies, but none of those things really kind of get at to the question, what exactly is science? All of those things have been studied by science, but what is science and what does it do for human beings? We're going to start to answer that question in the next couple of minutes of this video, but by any means we will not get anywhere close to the answer. Hopefully by the end of the course we'll have a pretty good definition for ourselves going forward about what science is. The National Science Teacher Association put together a list of things they considered to be part of the nature of science back in the year 2020. I provided that list here, and I'm going to go through and discuss a few of them with you because I do think they do a good job of providing some of the characteristics that are inherent to all scientific pursuits. The list is as follows. Some of the nature of science is scientific investigation uses a variety of methods. Scientific knowledge is based on empirical evidence. Scientific knowledge is open to revision in light of new evidence. Science models, laws, mechanisms, and theories explain natural phenomena. Science is a way of knowing. Scientific knowledge assumes an order and consistency in natural systems. Science is ultimately a human endeavor, and science addresses questions about the natural and material world, and only questions about the natural and material world. We'll take a little bit deeper dive on these topics in the next few minutes of this video. The first bullet point on that nature of science list that we just looked at was that science uses a variety of methods. And a new student of science might ask the question, well, doesn't all science use the scientific method? Isn't what I was taught all the way through grade school, that science relies on this very straightforward method that says an observation is made, a question is asked, a hypothesis is formed, an experiment is performed, a conclusion is came to, and those results are reported to the grand public. That's how we were all taught science is done, and that's what something makes something scientific. If it follows a scientific method, it is science, right? Well, I'm here to tell you that you've been lied to, that science in general is not as clean-cut as the scientific method makes it sound. Do we follow the scientific method at points during science? Absolutely. Do we form hypotheses, ask questions, make experiments, and come to conclusions? 100%. Does this happen in a neat, ordered path every time? Almost never. What really happens is some scientist gets curious about something. It may look more like this. Some scientist gets curious about some natural process or some natural phenomena, and they want to know how and why it works. And so they will go out into the community and try to figure out what is already known about that process. They may look up articles, they may talk to other scientists, and they start to gather information about what we already know. After that, they may try to figure out, okay, what do we not know about this process? What can we learn? And that's where they start to design an experiment. And what we often find happens is that experiments go wrong to begin with. So something has to be tweaked with the experiment, or the goals of the experiment have to be changed a couple of times. After numerous amounts of trial and error, something oftentimes, maybe not always, but oftentimes finally clicks, and then we can design an experiment to give us some new knowledge about how a process works. Once an experiment is designed and gives us some new knowledge, it's still not going to be accepted until that experiment is shared out to others and others can replicate those results on their own. And so we see that this scientific method that we've learned over the years in our different classrooms is somewhat a part of the overall process that is science. There are chunks along the way where we design experiments and interpret results. But those experiments are embedded within a large framework of communicating our results and letting our knowledge go out into the world and then come back to us revised with feedback. That is a big important part of science that the scientific method does not really kind of touch. To that same point, we observe all branches of science using their own observation techniques, their own tools, and a variety of methods to come to their conclusions. For instance, biologists famously use microscopes to observe the function and structure of cellular life and other microorganisms. However, the chemist doesn't have very much use for a light microscope because atoms and molecules are too small to be seen with that tool. On the other hand, astronomers use telescopes, which allow us to see big things on far off distances. Again, telescopes are not very much used to either the biologist or the chemist. Geologists use seismographs to measure the intensity of earthquakes, but those seismographs won't tell us very much about the intensity of earthquakes on another planet like a radio telescope might. So this is just a short point to make. Science can't proceed by this simple, constrained scientific method because all different types of science require their own individual methods to gain new knowledge. One of the most enduring hallmarks of science and scientific knowledge is the fact that it is based on empirical evidence and open to revision in light of new evidence. One of my favorite historical science figures is Dr. Richard Feynman, who was a brilliant physicist who worked at the University of California in the 40s, 50s, and 60s, and did some work on the Manhattan Project as well. If you've watched Oppenheimer recently, he was also a very good science communicator. He did a really good job of talking about the importance and impact of science on society and culture. He gave a really good quote here. This is one of his more famous quotes about what science is and how it proceeds. And it says, in general, we look for a new law by the following process. First, we guess it. Then we compute its consequences of the guess to see what would be implied if this law was guessed right. Then we compare it to the result of the computation to nature with experiment or experience, compare it directly with observation to see if it works. So to condense that down, he's saying most science does start along the path of we make a hypothesis and then we design some experiment to determine if our hypothesis is right. And what he says next is really the impactful part. If it disagrees with experiment, it is wrong. And that's a really easy to make statement. It makes sense, but it's impactful because that is always the truth in science. If it disagrees with the experiment, it is wrong. There's no way to talk your way out of it. There's no way to make yourself sound right. If your prediction does not predict what happens empirically in the natural world, then your answer is not correct. And we always take that to be the case. That's why science has to be shared out and replicated, because if those results are not replicable, then your results are not empirical and your results are not scientific. It does not matter how beautiful your guess is. It does not make any difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it is wrong. The next bullet point we see on the list from the Science Teachers Association about the nature of science is that science is a way of knowing. So science is one of the ways that humans know things, the ways we gain knowledge. That doesn't mean it is the only way of knowing things. We may use rationalism or appeal to authority to know things as well. Science can't tell us what is right or wrong morally. Science can't tell us what is or is not against the law. So there are many ways to know things, and science is one of those ways to know things. The last nature of science point I want to touch on in this introduction video is the fact that with all of that said, with Dr. Feynman's great quote about how if it doesn't agree with the experiment, then it is wrong, it is helpful to keep in mind that at its core, science is a human endeavor. And by the nature of science, we always try to strive to eliminate any bias in our testing. We want to have complete objectivity when we are performing science. That is impossible, however, because science is done by people. Data from experiments is interpreted by people. The communication and sharing of that knowledge has to be done by people, even though they are essential functions of science. That helps to validate those findings, it helps to validate those methods, but it does not always eliminate everything. So it's important that we are always sharing and communicating, and it's important that we are always open to revising our ideas in light of new evidence. One more thing I would like to address about the nature of science in this introductory video is the difference between the perception and the actual definition of laws and theories in science. Most everybody can give a pretty good explanation of how observation and hypothesis work, but many people have a misconstrued idea of how hypotheses then become laws and theories, and even what laws and theories are. Let me explain. We see a deflated or a half deflated basketball here on our left. Most Americans probably have had this observation in their life. They've picked up a deflated basketball. We know that if we kind of squeeze that deflated basketball, there's probably some air still trapped inside, just a little bit, and that if we squeeze it, we'll start to feel some pushback as we get it smaller and smaller and smaller. And so at that point, as scientists might want to make a hypothesis. Why does this happen? Why does putting more air into the basketball make it feel firmer? Why does letting some out make it feel softer? Why does squeezing it again make it feel firmer again? And so they may design some tests to test different reactions of the basketball, taking air out, putting air in, squeezing it, stretching it, heating it up, cooling it down. And in doing so, they are observing the natural world and they're doing science. And they may arrive at a couple of different answers or conclusions. And they could be different ones. They may arrive at scientific laws. Laws explain the behavior of natural phenomena. They explain behavior that happens over and over again. The gas laws give the behavior of a gas in a container. And we can see the gas laws are mathematical formulas. And these formulas basically just say that if you decrease the volume of a container, the pressure of the gas inside will go up. If you increase the volume of a container, if you make it bigger, the pressure of a gas inside will go down. If you increase the temperature of a gas in a container, its pressure will go up. If you decrease the temperature of a gas in a container, its pressure will go down. If you take a birthday balloon and blow it up and put it in the freezer and just leave it for 5 minutes, you can come back and take the balloon out and it will have deflated because the pressure of the gas that you put inside has gone down due to the temperature going down. Those laws explain those behaviors that happen every single time. But they don't explain why. Laws don't try to explain why something occurs. Theories are scientific explanations for the reasons of occurrence of natural phenomena. The kinetic molecular theory explains the behavior of gases. It says that matter is made of tiny little particles, and when they're in the gaseous form, they bounce and zoom around. Pressure comes from them hitting the side of their container and expanding force back outwards. The smaller you make it, the more times they hit the sides of the container, and the higher the pressure is. So that is an explanation of the nature of that behavior of the gases in the container. That's what a theory is. Furthermore, we tend to use the word theory wrong in everyday language versus scientific language. Notice I said that theory is well accepted. That is the whole point of a theory in science. Theories are our best explanation of a natural phenomena with the evidence that we currently have. Theories are accepted as truth as far as science knows. So when you hear somebody say, oh, blanky blank is just a theory, that's actually the wrong way to use the word, because in science, theory means something is accepted. There is no such thing as just a theory. It is a theory. That's a good theory. It's been tested and approved. That's what the word theory means. And so here we see just a short list of the differences comparing theories versus laws. Theories are based on repeated observation and scientific investigations. If new information doesn't support a theory, theories must be modified or rejected. Scientific theories attempt to explain why something happens, and scientific theories are usually more complex than scientific laws and may contain many well-supported hypotheses. Whereas, on the other hand, laws are observations of similar events that have been repeatedly observed. They're a little bit more simplistic. They're the mechanics behind nature that happen over and over and over and over again. If many new observations do not follow the law, the law must also be rejected. Scientific law states that something will happen. It doesn't try to state why it happens or how it happens. It just says this happens, this is the order of nature, it happens this way every time over and over again. That's what laws state. And a scientific law is usually based on one well-supported hypothesis stating that thing will happen this way every time. It's that when we see it, it doesn't happen that way every single time. That's when the law must be updated. So before we move on and talk about the three branches of science that we're going to be studying over the course of the semester, I want to talk about one last little misconception that we see people have about science, and that's the difference between science and technology. A lot of people think they're kind of one and the same thing, that, for instance, a piece of computer equipment or a camera, things that you see in the pictures, could be considered science themselves when they are instruments or tools that science has helped us produce. Science is the knowledge and the organization and the systems that are used to understand and order the natural world. We can use the knowledge that we get from those systems, that we get from science, to produce technology, and technology helps us interact with that natural world in ways beyond our own natural abilities. And as promised, we'll spend the last bit of this video here talking about the branches of science that we'll talk about over the course of our semester. I am classically trained in chemical science, and so that's the one we start with. We'll do chemistry first. Chemistry is the study of matter. We talk about what is matter made of, that being atoms and molecules. And we also talk a lot about the characteristics of matter. We talk about how we determine size and color and density, and then of course reactivity. How do the atoms and molecules arrange themselves into new substances? How do we get things like fire and colorful fireworks displays like you see behind us, and all of the great medicines that we have access to today? So we'll try to do some of those investigations in our chemistry unit. After we do chemistry, we also do biology, and biology, of course, is the study of life. We'll talk about the cells, the composition of organisms. It studies the behaviors of organisms, the characteristics of organisms, their classification, and their interactions with their environment. And in our biology unit, I like to take a look at the cells and their cell structure. We take a week look at genetics, and we do a week on viruses and bacteria, and then we do a week on ecology, that how organisms are interacting with their environment. We'll also do a physics unit, and physics is the study of energy, motion, force, space, and time. Physics measures the interactions between energy and matter, how energy is transformed into and out of matter. Physics concerns itself with things like velocity, acceleration, electricity and electrical force, gravitational force and gravitational motion, as well as nuclear force and nuclear reactions. And we'll take a look at some of the basic part of physics during that part of our unit. We'll also talk about, again, along the way, we'll talk about how to avoid and identify pseudoscience. And I've got a couple of good examples here. If you've never seen the picture at the bottom there is the guy doing the experiment he thought was going to prove the world was flat. We've got a ghost hunting show up there on the History Channel up top. So we'll talk a little bit about, along the way, about how to avoid getting caught up in pseudoscience misinformation, and how you can learn to identify it when it's not so quite on the nose.